Good morning, everybody. Today I'm going to talk to you about continuity. Now, continuity in mathematics is one of those words which has a very specific definition, which I'll get to in a second. But I just want to go over conceptually what it means before I get into specifics. And sometimes I find, as opposed to telling you what it is, sometimes easier to tell you what it's not. And the opposite of continuity would be discontinuity. And I just want to show you an image of several types of functions that are discontinuous. So here you have this first one, which has what we call a point discontinuity. There's like a break in the graph. It's not continuous. Here we have something that has jump discontinuity because this function has this thing where it jumps from one piece to the other. Very popular with piecewise functions. Down over here in the lower left, we have infinite discontinuity, whereas somewhere in the graph it breaks and goes up to infinity, or negative infinity for that matter. And then we also have what we call removable discontinuity, which is similar to the first one, point discontinuity, where there's a hole in the graph somewhere, but that hole is filled in somewhere else. That hole is removed and placed somewhere else. That's where we come with the term removable discontinuity. Okay, so these little images show you some things that are discontinuous. And a continuous function is important to us in mathematics because we can say so much about it. A whole different set of rules apply, things that we're going to get into, especially here in the calc part. So let's get to what continuity is. So we have a very specific definition for something that is continuous, a function that is continuous. A function f is continuous at a point C for any C value in the domain of f if, and that's not a misspelling, I'll come back to what that if with the double F's mean. There's three criteria. Here are the three criteria. So if you want to pause and then just jot these guys down, very specific definition. And depending upon when we get back together again, or if we don't until next year, there will be portions of calc exams where you're going to have to know things like specific definitions and theorems and such. So you have to be able to regurgitate this. All right, so I'll tell you what each piece means. The first says the value that we're plugging in for x is defined. All right, we don't have any holes. We don't have any infinities. The second thing is the limit exists. Now, if you remember when we did limits back in the beginning, I always said the value and the limit are not dependent upon one another. Now, however, if they are the same, if there is a sort of, I don't want to call it dependency, but if there's a correlation there, if the limit equals the value, then the function is continuous. Some people say that this third criteria is the most important of the three, and sometimes you can even just do this because if you have a value of C, that takes care of the first one, and if you have a value for the limit, that takes care of the second one. All right, so think about this. The limit exists. Now remember, that means it approaches the same thing from the left and the right, and the value is defined. So what kinds of things are continuous? I showed you some pictures before of things that aren't continuous. So some things that aren't continuous would be are continuous. I'm sorry, I said that backwards. A line, the sine or cosine function, a polynomial, an absolute value function. Something that's not continuous would be like a step function, the rational functions. You might remember them. They were the hyperbolas we drew earlier in the year, the things that look like this. The tangent graph, they're not continuous all. So up here in blue, I have what I call the KISS definition. KISS, keep it simple, stupid. F of x is continuous if you can draw it without lifting your pencil. That is not formal in any kind of way, shape, or form. However, people do find it helpful to think of it this way. If I can draw the graph without lifting my pencil, the graph itself is continuous. The function is continuous. However, I want to make sure we're perfectly clear on this. When I ask you to regurgitate the definition, I'm asking for the three criteria. That's the definition. The KISS is just something easy for you to remember. Okay, now before I start getting into continuity a little bit more, I want to backtrack for a quick second. I talked about this if with double F, and it's not a typo in any means, shape, form. What it does mean is it means if and only if. It's referred to as a biconditional in logic, and it represents an extremely strong statement. Biconditional means that logistically it works both ways. Okay, that if these three things happen, the function's continuous. And if the function's continuous, those three things happen. All right, so if you ever see if with the double F's, your math teacher's not doing something crazy. He's saying a very strong, logistically strong statement. Okay, now back to continuity. All right, I want to determine when f of x is continuous if f of x equals this. So then the question is, all right, what can't you have? Now, some of you people took Algebra 2 last year, like, all of you, and you had questions that looked like this that were asking you about the domain, and it's really kind of the same thing. What values of x in the domain would be bad? And in this case, since it's a fraction, it's when the denominator equals 0. So let's take a minute. Let's find out when the denominator equals 0. So whenever you have a rational function, that's what you're doing. It's like as if you're looking for vertical asymptotes or points of discontinuity from earlier in the year. See, it's all kind of like together. All related. All right, here we go. So then the x values would be -2 and -3. That's where it's discontinuous. That's where the discontinuity happens. So that means we're continuous everywhere else except those two values. Now somebody might point out, but you have an x plus 2 here. Can't that cancel with the x plus 2? Yeah, that's great. That's nice. I'm so glad you saw that. It means nothing. If the denominator equals 0 for these two values, that's discontinuous, continuous everywhere else. So how do we mathematically say this? We could say something like this. F is continuous, if you can, for all values of x that are real numbers, that's our domain, except, so x cannot be equal to -3 and -2. I like to go in size order, that's why I put the -3 first. So f is continuous for all values of x that are real numbers, except x cannot equal -3 and -2. And I want you to start getting used to writing the crazy symbols for, that's real mathematics when you're writing those symbols. Okay, so whenever you see a rational function, look for the denominator equal to 0. Think about the things you can't have. The answer, what can you have? All right, now let's look at some other things. Piecewise functions. Now, if I can just jump back for a quick second here. Boop. I said some examples, like a line or a polynomial. Those kinds of, what we group together polynomial functions, technically a line is a polynomial, that they are continuous all the time. So now I'm going to my question here. The x squared minus 3, polynomial, continuous. The -4x plus 2, a line, which is also a polynomial, continuous also. So independently, the little pieces are continuous. The big question is, do the pieces connect? Do they connect? Now, in order to figure out if they connect, we're going to look at what happens when x equals 1. Now, when x equals 1, that's the connection piece. We're going to see if they're the same. Now, I'm going to write it out specifically, technically, all the math stuff. So, if I'm going back up here to the formal definition, is the value defined? All right, so let's look at, is the value defined? Does f of 1 have a value? Sure, if f of 1 is a value, you plug it in over here. You get 1 squared minus 3, which is -2. So it has a value. So it meets the first criteria of continuity. The second part is, does the limit exist? So does it approach the same thing from the left and right? And that's the connection piece. That's the piece I was talking about a minute ago. Do they connect? Do they approach the same thing from the left and the right? All right, so let's look at that. So the limit as we approach from, let's start with the left of the function. Now left, if you recall, is less than. All right, and the less than part is the top part right there. The x squared minus 3. And that equals -2. All right, so from the left it works. Let's see if it works from the right, and we're going to hope that that number is the same. And from the right, that is the greater than side. That's -4x plus 2. And when you plug 1 into that, you get -2. So then since these two numbers are the same, that's telling you the limit as x approaches 1 exists. And it equals that number. Check. Now the third criteria was, does this number, the limit number, equal the same thing as the value? And look at it. They all equal -2. So what that is saying is it meets the third criteria that the limit as x approaches 1 of the function equals the same thing as f of 1. They both equal -2. That's the third criteria. All right, so met all three pieces of the criteria, so it connects, and independently the little pieces are continuous. So what's that mean? F is continuous, I'm going to abbreviate here, for all values of x without any exceptions. Is good. All right, let's look at another piecewise function, and I'm going to run through those three criteria because you should be looking at the three criteria. Is the function's value defined? All right, well, hold on a second. Independently, we've got a polynomial here, we got a polynomial here, so they're okay. We just need to find out if when x equals -1, is it continuous? Sorry, I had a little invader of a dog I had to get out. Here we go. Nothing like working from home. So the first thing I want to find out is, what is f of -1? Oh, wait, it's not here. There's no part where this, it's undefined. What am I trying to say? So my dog all threw me off, guys. Undefined. So that means right there, we know that this function is not continuous when x equals -1. Continuous at other places, because again, 6x cubed minus 9, polynomial, continuous. X plus 8, continuous all the time. So this is a little break in a graph, sort of, but this would actually be a hole in the graph. So, and I don't need to, once it breaks, I don't need to worry about the other three criteria. I could say right then and there, f is continuous for all values of x that are real numbers, except -1. Oops, here we are. All right. Oh, we got a three-parter piecewise. Again, look at the independent pieces first. 9 minus x, it's a line, continuous. 2x, also a line, continuous. 4, that'd be a constant function, a horizontal line going back and forth, still continuous. All right, now let's run through the three criteria. All right, the 3 right here, x equals 3, that's the number we need to look for. So let's first see, all right, the first piece of the criteria, what's f of 3 equals? Well, it equals 4. That's what this part here tells you. When x equals 3, the y value is 4. All right, does the limit exist? What's the limit as x approaches 3 from the left? Well, from the left, that's the less than, that's 9 minus x, so that would be 6. Right? 9 minus 3, 6. All right, now let's look from the right. So from the right, it would be 2x, which also equals 6. So this tells me right there, since those numbers are the same, the limit as x approaches 3 of the function equals 6. So it meets the first two criteria. But what about the third? Does the value equal the limit? No, it doesn't. So it fails right at the third criteria, that the limit as x approaches 3 of the function does not equal that. Oh, no. Oops, I meant to put a 3 here, guys. Sorry about that. Let's make that a 3 so you can read that. All right. So these two were good. This one was not. All right. What's that mean overall? The function is continuous for all values of x. F is continuous for all values of x that are real numbers, except x cannot equal 3. All right. You know what I'm going to do? I'm going to skip over this one right here. There is another topic here that I want to get to, and that's this one. Now we have to find the value of k that makes f continuous. We need to figure out what do we need to do to make this work. That's what we need to do. So 3x plus 1, continuous. Kx, continuous, because it's like saying, like, this could be 3x, it could be 6x, it could be negative 1000x, which would make it a line, but we don't know what the value of k is. So we're going to need to solve. We're actually going to solve for something now. So the question is, do they meet? We need to make them meet. All right, so what's this mean? Let's look at that. X equals 1. That's where the meeting point. So when x equals 1, this top part up here would be 3 times 1 plus 1, which would be 4. If x equals 1 here, this would be k times 1, which just equals k. So once you've plugged in those numbers to each piece, then just set them equal to each other and solve. Oh, there's nothing else left to solve. That's it. Here's another one. Find the value of k that makes f continuous. So plug the negative 2 in, because that is the magic number. So we're going to have 3 times negative 2 squared plus negative 2k. All right, so what do we get here? That's going to be 4. That's 12. So we have 12 minus 2k. All right, this part right here, we're going to have negative k times negative 2 squared minus 2 times negative 2. And what's that going to be? That's going to be, let's see, negative 4k plus 4. Then we set the two pieces equal to each other and solve for k. Now by doing this allows the functions to be continuous. So let's see, I'm going to add that 4k on over. We get 2k, subtract the 12 over. We get negative 8, and k equals negative 4. There you go. Kind of rushed it there at the end on the last two examples. We were solving for the value of k that makes the independent pieces continuous. But they are kind of like, just plug the x values in that they're questioning you about and set them equal. Not as, how can I say this? It's not as specific of a task, I could say that, as to when you're proving something is continuous or finding when it's continuous by running through the 3 criteria. All right, ladies and gentlemen,